Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last few lectures, we have been dwelling on very important topic which is on transition metal sigma alkyl complexes. These complexes are of prime importance as they are important intermediates in many catalytic cycles, and we were looking at various synthetic strategies required for preparing these complexes. In the last lecture, we looked at 4 different methods that are used in making these complexes. They involved oxidative addition, metallate acylation reaction, as well as sigma pi rearrangement type reactions. These reactions were, however, slightly different from the first 4 reactions that we had discussed, which involved metathesis reactions, insertion reactions, as well as metallate alkylation reactions. Now, having covered all of the synthetic methods available for preparation of transition metal sigma alkyl complexes, we are going to move over to something very interesting in this part of the lecture. We are going to talk about properties of transition metal sigma alkyl complexes. Now, these complexes initially were thought that they are thermodynamically unstable as they were very difficult to prepare, but later on it was found that they are indeed thermodynamically stable, but their instability arises from their excessive kinetic reactivity. Hence, preparation of binary transition metal alkyl or aryl requires challenging conditions. Or transition metal aryl So, having discussed all the synthesis method, in this we are going to talk about properties of transition metal sigma organyl complexes. Initially, the transition metal sigma organyl complexes were thought to be thermodynamically unstable, but later it was found that these complexes are indeed thermodynamically stable, but their reactivity arises from their kinetic lability, and that it is a challenge for preparing them. In this regard, binary transition metal alkyls and binary transition metal aryls pose a great challenge preparatively. However, they are often prepared as solvents. For example, here Cl3 reacts with Grignard reagent in presence of THF as solvent, giving this triphenyl chromium tris THF, where THF is a solvent molecule. Now, these reaction without the solvent, only compounds of this type M or N are homoleptic, are called homoleptic metal alkyls. These are indeed very difficult to prepare, and as a result these cannot be prepared in most of the cases, and in many of them metal sigma alkyl or sigma aryl complexes are prepared along with the solvates, as has been shown over here. Apart from the solvent molecule, as was seen in the last slide, transition metal compounds sigma alkyl complexes can also contain other ligands. Contains additional ligands. Like eta 5, C5, H5, carbon monoxide, PR3, halides. For example, PTCl4 with this Grignard reagent, methyl magnesium iodide, gives this 4 PT CH3 whole 3 PTI tetramer compound. The structure of this is of a Cuban type. Of this is called heterocubane. Type cluster. Now, what is coming out that homoelectric sigma alkyl complexes of transition metal are indeed a challenge to make, and most of the attempt in making them results in transition metal sigma alkyl complexes containing either the solvent molecule or other additional ligands, like as in the case observed for platinum compound discussed here. The other such examples contain other ligands apart from the metal alkyl moiety as shown here. For the following manganese compounds, so apart from this sigma alkyl ligand, there are other types of ligands that stabilize the overall metal complex. Now, here is a brief comparison between the transition metal as well as the main group metal carbon bonds strengths. For example, for the main group, EC metal carbon bond strength are sort of comparable to that of the transition metal bond strength. This can be elucidated by the metal carbon force constant of metal carbon bond for the following main group and transition metal compounds. For example, for tetramethyl silicon, the force constant is 2.93, which is a main group element. Tetramethyl germanium, it is 2.72. Tetramethyl tin, 2.25. Tetramethyl lead, 1.90. Okay. And tetramethyl titanium, it is 2.28. So, these are all main group elements, whereas this is a transition metal, and the force constant TMC bond of the transition metal is similar or lies within the range observed for the force constants of main group carbon elements. So, that sort of implies that the main group carbon as well as transition metal carbon bond strengths are of comparable capacity. For example, let us take a look at some bond energies of transition metal compound, sigma alkyl compounds, to get a value of their bond strength. So, bond energies are usually designated by dC in kilojoule per mole. Cp2 titanium diphenyl, the MC bond is 330 kilojoules per mole, whereas for titanium tetrabenzyl it is 260 kilojoules per mole. Zirconium tetrabenzyl is 310 kilojoules per mole. Tantalum pentamethyl 260 kilojoules per mole. Tungsten hexamethyl 160 kilojoules per mole, and let us say Cp platinum methyl about 160 kilojoules per mole. So, what it implies is that transition metal carbon sigma bond energy can vary a lot and lie within the range (120), which is a weak bond, to about 350 kilojoules per mole. So, the bond strength can be very weak to something which can be very strong. As a result, transition metal sigma alkyl complexes can show a varied reactivity. Another conclusion that can be drawn from this discussion is transition metal carbon bonds are weaker than transition metal heteroatom bonds. Transition metal heteroatom main group bonds like transition metal oxygen, transition metal chlorine, transition metal nitrogen, transition metal fluorine bonds. Also, the transition metal bond energy increases with atomic number. Increases so, as one goes down the group, the energy increases. For example, if one were to look between titanium and zirconium, zirconium being lower in the group has higher bond energy. Similarly, one can look at another example. For example, between pentacarbonyl, manganese, methyl, which has 150 kilojoules per mole, and corresponding the heavier analog pentacarbonyl, rhenium, methyl analog has 220. Here too, on going down the group, the bond energy increases, and this is what has been discussed over here. So, the transition metal carbon bonds are weaker than transition metal other main group elements like the heteroatom halide chlorides, and also for transition metal carbon bonds increases with atomic number as one goes down the group. Now, a lot of debate has gone into understanding the reason for instability of transition metal complexes. As mentioned in the beginning of this lecture, that the initial belief of transition metal complexes being thermodynamically unstable was later on proved to be wrong, and what emerged out was the fact that the extreme instability of transition metal sigma alkyl complexes arises from their kinetic lability rather than their thermodynamic stability, and that brings us to an important juncture of the need for understanding them. So, the instability of transition metal compounds can be explained by their kinetic lability, and that brings us to this discussion on a very important reaction that results in decomposition of many transition metal complexes. And what I am talking about is this famous beta elimination reaction. Beta elimination reactions are reactions which occur for transition metal complexes leading to their decomposition. Hence, a suitable strategy involves understanding the beta elimination reaction and blocking pathways that suppress blocking pathways that allow beta elimination reactions. Now, let us take a look at what is this beta elimination reaction. Let us say for a transition metal alkyl group that has beta hydrogen So, this is the alpha hydrogen and this is the beta hydrogen as it is located on the beta carbon chain. Now, the sigma bond of the hydrogen beta hydrogen or hydrogen located at the beta carbon gets attracted or interacts with empty metal d orbital as is shown here and proceeds to decomposition via a cyclic transition state as being shown here. Whereby this beta hydrogen is seen interacting with the metal orbital via a 4-member transition state leading to the formation of a metal hydride and an olefin bound to the metal and gradually this olefin bound to the metal eliminates from the metal center leading to a metal hydride complex and free olefin. And this reaction is called beta elimination. Beta elimination pathway is present in many transition metal sigma alkyl complexes that contains beta hydrogen and which leads to decomposition of many transition metal alkyl complexes giving metal hydride and olefin and hence results in instability of transition metal sigma alkyl complexes. In this lecture, we have looked into various properties of transition metal sigma alkyl complexes. We have looked into the bond strengths of transition metal sigma alkyl complexes and how they vary across the group as well as how they compare alongside their main group counterparts. We have also looked into the various decomposition reactions that are responsible for conferring instability to transition metal sigma alkyl complexes and that many of which are of kinetic origin. Now, with this we are going to go over to some very interesting aspect in the next lecture which would deal about how to suppress beta elimination reactions. Remember, if beta elimination reaction be a nuisance as it promotes decomposition of many transition metal complexes, well, if somebody finds a way to inhibit this beta elimination pathway, then that would lead to more stable transition metal sigma alkyl complexes. With that being in mind, the next lecture focuses on various strategies aimed at stabilizing transition metal sigma alkyl complexes through suppression of beta elimination pathways. We are going to take that up in my next lecture. Until then, I hope you have enjoyed the current discussion in the present lecture and wish to see you in the next lecture. Thank you.